This is the second half of section 5.2. We've got two more topics to go, multiplicities and similarity. There are two types of multiplicities, the algebraic, which I abbreviate as AM, which is the multiplicity of lambda as a root in the characteristic equation. I'll show you what that means with an example. And the geometric multiplicity, GM, is the dimension of the corresponding eigenspace. And we can show, but we're not going to, that the geometric multiplicity is always less than or equal to the algebraic multiplicity. And when they're equal, good things happen. So let's just start with a super easy example. Suppose A has characteristic equation this. This is the characteristic equation. Let's fill in the table. We're going to write down the eigenvalues and the algebraic multiplicities. So the eigenvalues are the roots. So think of this as lambda minus 1 squared, lambda minus 0 cubed, and lambda plus 2 to the 1. So the eigenvalues are the roots. So 1, 0, and negative 2. The algebraic multiplicities are the exponents over each factor. So 1 is a root twice. So we say it has algebraic multiplicity 2. 0 is a root 3 times, and negative 2 is a root once. So that is algebraic multiplicity in a nutshell. Okay, now let's look at both algebraic and geometric. Suppose A is this matrix. Find K so that the geometric multiplicity of lambda equals 5 is equal to the algebraic multiplicity. So we want the GM equal to the AM. 5 is an eigenvalue because A is diagonal, and so the eigenvalues are 5, 3, and 1. So I've written down the matrix A minus lambda I, and I just subtracted lambda on the main diagonal. So the first thing we're going to do is find the algebraic multiplicity of lambda equals 5. So we have to write down the characteristic equation. Since A is diagonal, determinant, hang on. Okay, I'm back. I'm sorry about that. I didn't mean diagonal anyway. What we want here for the characteristic equation is determinant of A minus lambda I equals 0. A is triangular, A minus lambda I is triangular, so the determinant is the product of the entries on the main diagonal. So we've got a 5 minus lambda twice. 5 minus lambda squared. We've got a 3 minus lambda, and we've got a 1 minus lambda. And my pen stopped writing. Okay. Let's see if I can erase 1 minus lambda. All right, technical issues, hang on. Okay, usually when that happens, if I change the ink to something funky, it stops doing that. So yeah, that seems to be working. So there's my characteristic equation. The algebraic multiplicity of lambda equals 5 is 2. So that's the exponent over the 5 minus lambda factor. Okay, now we're going to do the GM. We want the GM to be 2 also, because we want the GM to be equal to the AM. So we need the dimension of the null space of A minus 5I to be 2. Now, remember about dimensions and null spaces. Each free variable in the equation AX equals 0 gives you a basis vector, so add ones to the dimension. So what we need is 2 free variables. We want 2 free variables in the equation A minus 5I times X equals 0. Because each free variable will give us a basis vector, and we want to have 2 basis vectors because we want the dimension of the eigenspace to be 2. Okay, so this is A minus 5I. I've augmented with 0, and that is equivalent to, I only need to go to echelon form to look for free variables. I don't have to go to reduced echelon. So I'm just going to leave the top row alone. And then I'll multiply the top row by -1 and add it to the second row. 0, 0, k minus 6, 1, 0, and then I'll leave row 3 alone, and I'll use row 3 to kill row 4. Okay, so I've got pivot, pivot. So two variables are leading. They can't be free no matter what. X1 is free, so I need X3 to be free because I want two free variables. So I need K equals 6. Okay, so here's one for you to try. You should pause the video, P and P, pause and practice. For this matrix A, write down the matrix A minus lambda I, write down the characteristic equation, fill in that chart, and find the geometric multiplicity of lambda equals 3. Okay, so I'm going to do this one with you. Write down the matrix A minus lambda I. So 2 minus lambda, 0, 0, 0, 5, 3 minus lambda, 0, 0, 9, 1, 3 minus lambda, 0, and then need to go this a little bit longer there, 1, 2, 5, negative 1 minus lambda. All right, write down the characteristic equation. The characteristic equation is determinant A minus lambda I equals 0. Since this is lower triangular, but it doesn't matter as long as it's triangular, then the determinant will be the product of the entries on the main diagonal. So let's see, I've got a 2 minus lambda, I've got a 3 minus lambda twice, so 3 minus lambda squared, and then a negative 1 minus lambda. And what I'm going to do, instead of writing negative 1 minus lambda, I'm going to factor the negative 1 out and put it here, and then put 1 plus lambda. It's a little cleaner and a little easier to see the eigenvalues that way. So I factored the negative 1 out of that factor. So fill in the chart. The eigenvalues are 2, 3, and negative 1, because I need to set this equal to 0, that equal to 0, and that equal to 0. Algebraic multiplicities are going to be the exponents over each factor. So 1, this shouldn't be a 3, huh? This was 3 minus lambda squared, so that's a 2, and that's a 1. All right? Find the geometric multiplicity of lambda equals 3. We know the algebraic multiplicity is 2, so the geometric multiplicity is either going to be, the geometric multiplicity is always less than or equal to the algebraic multiplicity, so it's either going to be 1 or 2. All right, so what we need to do is reduce A minus 3I augmented with 0, and look and see how many free variables we have. And so that's the matrix. We've got A minus lambda I written above. If you put 3 in for lambda, you get negative 1, and then all zeros, 0, 0, 0, 0, and then 5, 0, 0, 0, 0, 9, 1, 0, 0, 0, 1, 2, 5, negative 4, 0. That looks like a minus sign, so take that out if I can. Okay, we need to get this to echelon form, not reduced echelon form. So I'm not going to walk through all the steps with you. You need to verify that you can get this. Negative 1, top row stays the same, 0, 0, 0, 0, and then 0, 1, 0, 0, 0, 0, 0, 5, negative 4, 0, and then all zeros on the bottom. It only takes a couple of steps, but you should be able to do that. So I've got pivot, 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 one free variable, the GM is equal to 1. All right. So last topic, similarity. And we're going to use similarity in the next section. A and B, if they're n by n matrices, A is similar to B if there's an invertible matrix P such that A is PBP inverse. PBP inverse. So if A is similar to B, B is similar to A, so you can just say they're similar and there's no confusion. Here's an example. I've given you a matrix A and I claim it's similar to B because with the matrix P equaling this matrix, A is indeed PBP inverse. Now, the hard way to check that statement is to compute PBP inverse. The easier way is to multiply both sides of this equation by P inverse. So on the, by P. So on the right, multiply by P. On the right, multiply by P. That gives you AP is PB. So this is a quick way to check if the two matrices satisfy the similarity requirement. So let's just compute AP, and we get 2, 3, and then 2, 6. That's -2 plus 8, yeah. All right, and then PB, I get 2 going across the top, 3, and then I get 2, 6. Little shortcut here is when you multiply by a diagonal matrix, what it does is it scales the columns of A. So 2, 2 is twice the first column. 3, 6 is 3 times the second column. So right multiplying by a diagonal matrix scales the columns of A. Left multiplying will scale the rows of A. All right, and then we're winding up here, but almost done. Important theorem, if A and B are similar, they have the same eigenvalues because they have the same characteristic polynomial, so the same eigenvalues. However, they don't necessarily have the same eigenvectors, okay? Also, the theorem doesn't go in the opposite direction. If they have the same eigenvalues, then they're not necessarily similar. And so that's this statement. If A and B have the same eigenvalues, they're not necessarily similar. And I put an example at the end. And let's just look at this statement about not necessarily having the same eigenvectors. I took the two matrices from above, A and B, so we know they're similar. B has eigenvalues 2 and 3. So A has eigenvalues 2 and 3. So let's find an eigenvector. Consider this vector here, 1, 0. This is going to be an eigenvector for B. And let me show you that. If I multiply B times 1, 0, I get 2, 0, which is twice 1, 0. So V is an eigenvector for B. But now we'll see that V is not an eigenvector for A. So if I multiply A times V, I get 1, -2, and that's not equal to any scalar times 1, 0. So V is not an eigenvector for A. Okay. And then, so that's the end of the lecture. On this page, we've got a solution to practice 2. And then on the next page, some optional stuff, dynamical systems and Markov chains. The comic I just put in because it's got eigenvalues and eigenvectors, but I don't think it's a great comic, and I'm not even sure I get it. But maybe if you can understand it, or if you think it's funny, just let me know. And that is the end of section 5.